Welcome to Neural Nexus Academy. Today, we're diving into a really fascinating engineering explainer on limits, fits, and tolerances. Basically, we're going from the illusion of absolute manufacturing perfection straight into the messy but amazing reality of mechanical precision. Let's get right into it, because these concepts, they're literally the hidden foundation of every single physical product around you.
So we've got to start by shattering a pretty common myth. Imagine you need a solid metal shaft, and you ask a factory to make it exactly 50 millimeters in diameter. Can they do it? Like exactly 50 millimeters, right down to the microscopic level, every single time? Well, no way. It's impossible, because machines naturally have slight variations. Tools wear down, temperatures shift. Getting mathematically exact parts just doesn't happen in the real world. And that introduces a completely crucial engineering requirement: the need for acceptable deviations.
To navigate this, we're going to follow a quick 5-step roadmap for this explainer. We'll hit the perfect manufacturing myth, limits, tolerances, and deviations, analyzing shafts and holes, understanding material limits, and finally, mastering mechanical fits.
All right, Part 1, the perfect manufacturing myth. Let's lay down the basics. To establish a solid baseline when absolute perfection is off the table, engineers use our first core concept, basic size. Think back to that 50 millimeter shaft. That 50 millimeters, that's the basic size. It's the theoretical, exact dimension we use as a starting reference. Think of it like our ultimate anchor, right? A persistent zero line that all our complex calculations and acceptable boundaries are grounded against. It's the dream target, even if we know we won't hit a bullseye every single time.
So, since we can't hit that basic size perfectly, manufacturers have to set upper and lower boundaries. And we call these limits. They are the absolute maximum and minimum acceptable dimensions allowed for a product. So, your 50 millimeter shaft might be allowed to be as large as 50.02 millimeters or as small as 49.98. If a shaft rolls off the line anywhere inside that specific range, boom, it's a successful, acceptable part.
Now, if you take that maximum acceptable dimension and literally just subtract the minimum acceptable dimension, you get your tolerance. Tolerance is the total zone of acceptable variation. It's exactly how much wiggle room or error a design can safely handle without breaking down. And here's the real-world catch. The bigger the tolerance, the cheaper and easier it is to make. The smaller the tolerance, well, that requires way more precision, which means it gets expensive fast.
Moving right along to Part 2, limits, tolerances, and deviations.
Okay, now that we've got our vocabulary down, how do engineers actually write down these acceptable deviations? Well, there are two main systems. First up is the unilateral system. This is where the permitted deviations push the size strictly in one direction from that basic size. So it's either all positive, like plus 0.04 and plus 0.02, or all negative. Then you've got the bilateral system. This one allows for variation in both directions across the zero line, something like plus 0.04 and minus 0.03. It's basically saying, hey, this part can be slightly larger or slightly smaller.
Let's jump into Part 3, analyzing shafts and holes.
Going from just abstract numbers to actual physical parts that fit together, we usually look at two main things: the shaft, which goes inside, and the hole, which receives it. To keep engineering drawings from turning into total chaos, there's a strict visual rule. Lowercase letters always mean shaft calculations. So ES is the upper deviation of a shaft, and EI is the lower. Uppercase letters, those are strictly for hole calculations, using uppercase ES and EI. It's a really simple trick, but it means an engineer instantly knows if they're looking at the pin or the hole it goes into.
Now here's a concept that always seems to trip people up: the fundamental deviation. Simply put, out of the upper and lower limits, the fundamental deviation is the single one that sits closest to our zero line. Mathematically, it's the smaller of the two calculated deviations. For shafts, depending on the setup, this usually lines up with the upper deviation. For holes, it's usually the lower. Nailing down this fundamental deviation is key, because it acts as the primary anchor point for all the other math you're going to do.
All right, on to Part 4, understanding material limits. Let's get physical.
Instead of just looking at math on a page, let's think about the actual metal left on the manufacturing table. When we talk about the maximum material limit, or MML, we're basically asking, when is this part the heaviest? For a shaft, it's a no-brainer. MML means producing the absolute thickest, largest shaft allowed by the tolerance. But for a hole, it's literally the exact opposite. Think about it. Drilling the smallest hole possible means you're removing less metal, leaving the maximum amount of base plate intact. So smallest hole equals maximum material limit. Kinda wild, right? And we can flip the script completely for the minimum material limit. Now we want the lightest part possible. For the shaft, the minimum material condition is just the thinnest, most shaved-down shaft allowed. But for the hole, to leave the absolute minimum amount of material in that base plate, you have to bore out the largest possible hole. Once you grasp this inverse relationship for holes, reading engineering gauges becomes an absolute breeze.
Finally, let's bring it home with Part 5, Mastering Mechanical Fits.
Out in the real world, how these parts interact comes down to 3 primary types of fits. Number 1 is the clearance fit. This is where the smallest possible hole is still bigger than the largest possible shaft. It guarantees a gap so parts can spin freely like a wheel on an axle. Number 2 is the interference fit. Here, the smallest possible shaft is actually bigger than the largest possible hole. There's no way it's going in without forceful pressing or heating the hole to expand it. It creates a tight, permanent bond. And number 3 is the transition fit. This one lives in the overlapping gray area between the first two. Depending on the exact sizes manufactured that day, you might get a tiny bit of clearance or a tiny bit of interference.
Now, if you're engineering a critical system, you absolutely have to know the worst-case scenario when putting these parts together. To find the absolute tightest possible condition these two parts will ever experience during assembly, engineers calculate what's called the allowance. So the allowance is precisely the mathematical difference between the smallest possible hole and the largest possible shaft. You just subtract the maximum material limit of the shaft from the maximum material limit of the hole. That gives you the extreme boundary of tightness. If your allowance is positive, you're guaranteed to have at least a little clearance. If it's negative, you are definitely dealing with an interference fit.
As we wrap up this explainer on precision, I want you to look around your everyday life. Next time you forcefully snap the cap onto a marker pen and hear that satisfying click, ask yourself, which mechanical fit did I just experience? Yep, it's an interference fit. Everything from the gears in your car to the hinges on your laptop relies on these hidden principles. So, what other perfect objects in your life are actually masterclasses in engineered imperfection?